Alright, welcome to the early morning video. Let me check my inputs and outputs. So my output is messed up here, so I've got to fix that. Alright, so now my output looks good. Input's a little bit quiet. Not sure what's going on with that. I don't think it's been like that before. Maybe if I get down. Oh yeah, I think that's sometimes the exact right position of the microphone matters a lot, and I might be speaking more quiet than I normally do. But we're gonna move on to auto encoders. I introduced the auto encoders earlier in the book when discussing anomaly detection, but I did not want to enter into details on its inner workings because we had not seen what a neural network is yet. An autoencoder is a neural network architecture intended to produce the same output it gets as input. The first consequence is that it is not truly a supervised technique because in practice you do not need labels to use an autoencoder with a specific dataset. However, a neural network is a supervised learning technique. How do we resolve this? We will refer to this domain of use cases as self-supervised learning techniques. While there is no explicit label in the form of class or number to predict, we extract from our data some value that serves as a label to train a model. In our case, the label becomes the data itself, since we want the autoencoder to produce the same output as it gets as input. Furthermore, why would we do this? It seems like a total waste of time. The autoencoder is built using the encoder-decoder approach I referred to earlier. It has a particular characteristic. It is not just about producing the same output as it got as input, but it is about forcing the network to do it by encoding the input data in a specific intermediate latent space with lower dimensionality than the input data. Then we make the decoder reconstruct the input signal from the data it gets in the latent space. Effectively, what we are doing is compressing and decompressing the signal, but very likely with some loss. The goal of the autoencoder, though, is not to find a compression mechanism for the data, but to learn the internal patterns in the data that would allow it to perform such compression in a way that the loss is minimized when the decoder reconstructs the data. Effectively, it is learning how such data behaves. So let's do the classic tried and true feeding of this to ChatGPT. Alright, and I haven't done a video in a while. I use ChatGPT quite a bit, so it's buried. Oh, here we go. This is it.
The diagram you provided illustrates a basic architecture for an autoencoder, a type of neural network used primarily for the purpose of learning efficient encodings of data. Here's a detailed explanation of each component and how the process functions. Components of an autoencoder. Encoder. The encoder part of an autoencoder takes input data and compresses it into a smaller, denser representation, which is often referred to as the latent space, or encoding. This part of the network typically reduces the dimensionality of the data by learning only the most relevant aspects needed to recreate the input. Latent space. This is the core feature of an autoencoder. The latent space represents a compressed code that holds the essential information about the original input data. The effectiveness of an autoencoder often depends on how well this latent space captures the important aspects of the input data. Decoder. The decoder's role is to reconstruct the input data from the compressed form provided by the latent space. Ideally, the output of the decoder should closely match the original input, indicating that the latent space has successfully captured the key features of the data. Functionality of an autoencoder. Data compression. Autoencoders are trained to minimize reconstruction errors, differences between the input and output, which encourages the latent space to retain as much useful information as possible while discarding relevant details. Dimensionality reduction. By encoding data into a lower dimensional space, autoencoders can be used for dimensionality reduction, similar to techniques like PCA but with a more flexible, nonlinear approach. Feature learning. During training, autoencoders learn to identify patterns or features in the data that are helpful for reconstruction, making them useful for unsupervised learning tasks. Applications. Data denoising. Autoencoders can be trained to ignore noise in the input data, allowing them to reconstruct the clean original version of the data from noisy inputs. Anomaly detection. By learning to reproduce only the common features in the data, autoencoders can be used to detect outliers or anomalies which will have higher reconstruction errors. Data generation and imputation. Once trained, the decoder part can be used to generate new data instances or predict missing values by manipulating the latent space. Summary. Autoencoders are a fundamental tool in the field of neural networks, offering a versatile approach for learning representations and features of data without needing labels. Their ability to compress, denoise, and reconstruct data makes them invaluable in many applications across various fields such as image processing, natural language processing, and more sophisticated tasks like semi-supervised learning.
All right, and this is self-supervised learning, which probably is the same thing. When we discussed autoencoders earlier, it was in the context of anomaly detection. If something happens that produces a different behavior in our signal, the high chances are that the autoencoder that we have trained will not be able to reconstruct this new signal properly because it is not behaving as it expects. So the fact that we get higher than normal reconstruction loss at the output is the signal that there is an anomalous behavior. Autoencoders are also used, for example, to denoise data. You can feed the autoencoder with your data plus some artificial noise, but have as the target your data without noise. The autoencoder will learn how to reconstruct the data without noise. The autoencoder does not learn the noise unless it is overfitting. At inference time, once it receives specific data that contains noise, it will know how to reconstruct the data at the output, and this time without noise. All right, so here's another graphic.
The diagram you provided illustrates a specific type of autoencoder known as a denoising autoencoder. This model is designed to process data that has been intentionally corrupted by adding noise. The goal is to train the network to recover or reconstruct the original, uncorrupted data from the noisy input. Here's a detailed explanation of its components and operation. Components of a denoising autoencoder. Training data plus noise. The input of the denoising autoencoder is the original training data that has been corrupted by some form of noise. This noise could be anything from random pixel noise in images to synthetic errors in text data. Encoder. The encoder part compresses the noisy data into a smaller, denser representation in the latent space. The encoder learns to identify and ignore noise characteristics, focusing instead on the underlying patterns that represent the clean data. Latent space. This represents the compressed form of the input data. For a denoising autoencoder, the latent space attempts to capture the essential features of the original data, minus noise. Decoder. The decoder then takes this compressed encoding and attempts to reconstruct the original data, aiming to produce an output that is as close as possible to the original clean data before noise was added. Functionality of a denoising autoencoder. Noise reduction. The primary function is to reduce or eliminate the noise from the input data. This is achieved by training the network to ignore the added noise during the encoding process and to focus on reconstructing the noise-free aspects of the input data during decoding. Training process. The network is trained using pairs of noisy and clean data. However, in practice, often only the clean data is available, and noise is artificially added as part of the training process. The loss function used during training typically measures the difference between the decoder output and the original clean data, not the noisy input. Applications. Image processing. Denoising autoencoders are commonly used in image processing to clean up images that have been corrupted by factors such as sensor noise, transmission errors, or other forms of interference. Data preprocessing. Before performing tasks like classification or feature extraction, denoising autoencoders can preprocess the data to improve the quality and accuracy of a subsequent analysis. Robust feature learning. By learning to ignore random variations, noise, in the input data, denoising autoencoders can learn more robust features that generalize better to new, unseen data. Summary. Denoising autoencoders leverage the autoencoder architecture to perform the specific task of denoising input data. This ability to recover clean data from noisy inputs makes them highly valuable in many domains where data quality can significantly impact performance, such as medical imaging, speech recognition, and financial modeling. The process not only improves the usability of the data, but also enhances the performance of other machine learning models by providing cleaner, more accurate data for training and analysis.
All right, so we could train an autoencoder, but then we use the encoder and decoder parts separately in a targeting system. We could use the encoder as a dimensionality reduction component since it effectively compresses the input data into a lower dimensional space, latent space. Then you can train your model using the data in latent space format, produce some output, and use the decoder to bring it back to the original format. We will see various examples of this use case later in the applied examples section. So here's the next part. So there's latent space.
The diagram you provided illustrates a unique application of an autoencoder architecture integrated with another machine learning model operating within its latent space. This type of configuration is especially useful for complex tasks that require feature transformation or dimensionality reduction before further processing. Here's a breakdown of the setup and its potential applications. Components. Encoder. The encoder compresses the input data into a lower dimensional latent space. This encoding process aims to capture the most relevant information in more compact form, which can be beneficial for reducing noise and improving the efficiency of subsequent computations. Latent space. This component represents the reduced dimensional representation of the input data. It serves as an intermediary space where data is more manageable for processing, typically containing the essential features extracted from the input. Some other ML model. This component indicates another machine learning model that operates on the encoded data. The nature of this model can vary widely depending on the specific task. For instance, it could be a classifier, a regression model, another layer of feature extraction, or a predictive model. Decoder. The decoder's role is to reconstruct the original input data from the modified latent space, post-processing by the other ML model. This step is crucial to determine how changes in the latent space affect the reconstructed output, serving as a feedback mechanism to refine the encoder and the ML model within the latent space. Functionality and workflow. Data encoding. First, the encoder reduces the dimensionality of the input data, transforming it into a simpler form for processing. Intermediate processing. The transformed data is then used as input to another machine learning model that performs specific tasks, such as classification, clustering, or further transformations. Data decoding. Finally, the decoder attempts to reconstruct the original data from the outcome of the intermediate model, essentially testing how well the latent space and the subsequent transformations preserve or highlight important features of the original data. Applications. Feature enhancement for complex tasks. In tasks where raw data is too complex or noisy for direct analysis, using an encoder to simplify the data can enable more effective further processing. Dimensionality reduction for large datasets. When dealing with large-scale data, reducing its dimensionality can significantly speed up processing without losing critical information, making it manageable for other ML models. Data anonymization. This setup can be used to modify data in a way that anonymizes or secures it before further analysis, ensuring privacy or security by altering sensitive features in latent space. Integrated learning systems. In a multi-stage learning process where different models need to interact with each other, e.g., in a pipeline, integrating an encoder-decoder architecture with other models can create a more flexible and powerful system. Summary. This architecture effectively utilizes the strengths of autoencoders for data transformation and compression, combined with the versatility of machine learning models tailored to specific tasks. It highlights a modular approach where different components can be optimized independently yet work cohesively to achieve complex data processing objectives. Such setups are increasingly relevant in fields like bioinformatics, financial modeling, and multimedia processing, where raw data often requires significant transformation before it can yield useful insights.
All right, so for example, we will review that it may be convenient to transform log messages into a latent space representation. This representation is more compressed and will facilitate training another model for log prediction. This is one of the use cases we will see in the latent space because it is more compact and information rich. As a last step, because the output of that model is also in the same latent space, we can use the decoder to bring the log back to a human readable format. We will see this working later on. Autoencoders are fascinating architectures that allow us to manipulate and transform data into more compact and information-dense representations. Key takeaway: while autoencoders have some practical applicability for anomaly detection and data denoising, they are truly a data representation technique. They enable transforming the input data into different lower dimensional and more compact, efficient, and semantically aware space. All right, so the next section is transfer learning. So I'll advance the bookmark and take a quick break. All right, I'm back. So moving on. So moving on to a whole new section. This is the transfer learning section. Before we introduce a couple of other neural network architectures, It is the right time to introduce a new concept, extremely important in machine learning these days, particularly in deep learning. Let's start by emphasizing that the machine learning field is highly active and vibrant, partly because almost everyone has embraced the culture of sharing. Models and techniques have been shared with the community, usually in the form of open source, to benefit everyone, which has boosted innovation. There are many machine learning algorithms, implementations, frameworks, and model architectures fully available for anyone to learn and use. There is a human-to-human transfer learning that has enabled organizations to move faster, leverage existing knowledge, and build on top of it. If you want to build a model to recognize certain types of images, you can likely use existing architectures such as VGG and others without reinventing the wheel. Architectures that have been proven effective in similar environments. However, we can take transfer learning to the next level. Let's imagine a CNN that has been trained to recognize and classify different types of dogs in an image. The result of such a training process is a particular ML model architecture and a set of weights, probably hundreds of millions of them, that are optimal for such a task. Now let's suppose our task is not about dogs and cats. We need to build an ML model to recognize and classify different types of cats. When we train an ML model, remember that weights are randomly initialized, but which values they are initialized with ultimately matters to the success and result of the training process. So, intuitively, what do you think would be better for the new cat model? To initialize the weights randomly or initialize the weights with the value of the dog model? The weights in the dog model are likely closer to the target values since the model is already trained to do a similar task to the one we are now targeting. This intuition is correct, and it is called transfer learning. Leveraging trained models in similar tasks, which implies architecture and weights as the starting point of your training process for a new task. We can leverage the expertise the model has already built in to accelerate and produce better results in our tasks. So that makes sense. Like if your model already knows how to identify fur, if it already knows how to identify eyes and backgrounds versus foregrounds, that'll be useful. This transfer learning approach can be implemented with two approaches. Initialize the weights using the ones from the reference model and perform the full training from there. Initialize the weights using the ones from the reference model, keep a certain percentage of them fixed, and only allow training on a small subset. This is particularly applicable to CNNs, where the first layers of a CNN are mostly focused on extracting low-level features from the image, so you could argue that those weights are probably good enough for our new task. Because of that, it is a common practice when we need to train our new model to leverage not only the architecture of an existing model from the open source community, but also the weights it was trained on. In this way, specific layers of the model will not be trained, and the weights are just used as is from the downloaded model. Then some of the deeper layers, usually those more specific to the task at hand, are trained and the weights updated. This greatly simplifies the training process since the number of weights to train is much lower, and it enables the training to start from a point that is better than if it was completely random. Transfer learning is, therefore, a widespread practice because both it is technically possible and convenient, and because the community has aligned around a culture of sharing and collaboration with broadly available models in terms of architecture and weights. Key takeaway: transfer learning is one of the key capabilities of neural networks and saves a large amount of effort as it allows us to leverage other teams' work in the same or similar problems. All right, so next section is on transformers. We have introduced the concept of encoder decoder architecture, usually called SEQ to SEQ, as is frequently used to receive one sequence as input and produce another sequence as output, with potentially different sequence lengths between input and output. A clear example of applicability is language translation. These architectures usually leverage some form of recurrent neural network, very typically LSTM, which remember stands for long short-term memory. So it's a recurrent neural network that has an enhancement where it can remember for a longer period of time. Traditional recurrent neural networks have a flaw where their short-term memory is very low, but there is a more robust update to the neural network that gives it a longer short-term memory, and that's called LSTM. The decoder receives a compacted representation, the latent space vector, of the input sequence, which is all it has to generate the output sequence. For tasks such as language translation, one particularly challenging phenomenon is the ambiguity. The same word may have different meanings depending on the context. Somehow, it is necessary to provide machine learning models with the ability to pay attention to the keywords before or after that may help resolve the ambiguity. Therefore, a new mechanism was developed so that the decoder could have more explicit information on the importance of different words in the input sequence besides the latent vector. This may help determine the proper meaning and therefore the adequate translation. This mechanism was called attention. In combination with LSTM, attention mechanisms helped improve translation capabilities by feeding the decoder with new contextual information. I will not go into the details about the how. My goal for you is to understand that attention mechanisms enhance the ability to capture relevant contextual information, for example, to deal with ambiguous words. How is this relevant or useful in networking or clouds? Well, you could think of a model that could get a Juniper Junos switch configuration and produce as an output ooh, that's cool. That's really cool. An Arista switch configuration equivalent or vice versa. That is useful because you'll just have to take my word for it, but there are organizations some organizations will replace all of their infrastructure just to have consistency, and that's very expensive. But if instead you could get that same kind of consistency through machine learning like that, that would be really powerful. These are languages for practical purposes, like Spanish, English, or German are. Therefore, if anyone builds or tries to build such models, it is very likely that they will need to use some sort of attention mechanism. In 2017, a well-known and at that time controversial paper was released titled "Attention is All You Need." The central proposition was that it was possible to build encoder-decoder architectures for sequences entirely based on attention mechanisms without using recurrent neural networks like LSTM. The architecture proposed is referred to as transformers. Since then, many huge models have been produced following the transformer architecture. And I believe that's what ChatGPT is based on. That's what it's based on GPT-3, so ChatGPT, the GPT stands for GPT-3, which is the architecture, and the T stands for transformer, as far as I know. Generative transformer, I forget exactly. For now, keep in mind that a transformer is a type of neural network that is built using attention layers. And I just want to call attention to the fact that it kind of breaks down the is it anthropomorphism? I think that is what it is. Anthropomorphism. Yeah. So the attribution of human characteristics or behavior to these concepts kind of breaks down. They're not talking about attention in the same way, a human and a brain would pay attention. They're not talking about transfer learning in the same way that a human would learn a skill like weightlifting and then become better at something else like playing tennis because of that. So I would say be careful not to fall into that trap, because that's a very easy way to end up misunderstanding these concepts. So just keep that in mind, that this is all specific to machine learning, AI, and it correlates a little bit to real learning in the human brain. It's kind of based off of it, like neural networks and neurons. Neural, that doesn't come from nowhere, but it only goes so far. All right, so next section is Siamese networks. Combining more than one neural network in composite architectures makes it possible to address new problems. The case of so-called Siamese networks is an excellent example of that. As the very name indicates, it is an architecture composed of two, sometimes more, instances of the same neural network. The primary use cases are about verification. In other words, they are checking that two inputs correspond to the same entity. Let's say the same person in an image or the same signature, etc. The goal is not to specifically identify which is the entity, but to verify that it is the same in the two inputs. This is very useful in scenarios of face verification versus face recognition. In face recognition, the expectation is that you have trained a model that, as the output, will be able to tell when it sees a picture with your face that it is you, the person in the picture. Therefore, it requires the model to be trained with all the pictures of the people it should be able to recognize. Furthermore, when there is one more person, it needs to be retrained. Face verification, however, aims to verify whether two pictures correspond to the same person or not. You train the network to learn a similarity function, not to learn if you are the one in the picture. Let's imagine the use case of security access to a building. There are 100 people authorized, which the system has one picture of. Then when you try to access it, the system takes a picture of you and verifies one by one against those 100 pictures of whether anyone is very similar to you. If it is, then it will let you in. If you are a new employee and the system does not have your picture, it is as easy as adding your picture to the database. There is no need to retrain the model because What the model has learned is the ability to differentiate if two pictures correspond to the same person. And I will say, in the real world, I feel like there are better security solutions than that. Oops, and that's the wrong thing I pulled up. So I got to pull up the right thing, which is the snipping tool.
The diagram provided depicts a Siamese neural network architecture. This type of network is particularly useful for tasks that involve finding the similarity or relationship between two comparable things, such as images, sentences, or videos. Here's a detailed breakdown of how it works in its applications. Components of the Siamese neural network. Input pairs x1, x2 by 1, x2 by 1, x2. These are two input vectors or data points that need to be compared. For example, in face verification task, f1 by 1 by 1 and x2 by 2 by 2 could be different images of faces. Network A. This represents a neural network that processes each input. Crucially, the same network with the same parameters, weights, and biases is used for both inputs. This shared network ensures that the features extracted from both inputs are comparable. The network typically consists of several layers, convolutional, fully connected layers, etc., designed according to the type. Similarity function.
All right,
After both
sorry
inputs are
about
processed
that.
through network A, their outputs, feature vectors, are passed to a
So my headphones just lost the connection randomly. So sometimes that happens. Let's listen to it again.
The equation you provided is a fundamental concept for logistic regression, a statistical method used for modeling a binary outcome, where outcomes are typically labeled as 0 or 1. Let's break down the components of this equation. PPP. This is the probability of the occurrence of an event, like success, failure, yes, no.
Okay, so something weird happened there too. It's not reading. It's reading about an equation.
The equation you provided is a fundamental concept for logistic regression, a statistical method used for modeling a binary outcome, where outcomes are typically labeled as 0 or 1. Let's break down the components of this equation.
Yeah.
The
So
equation you provided is a fundamental concept for logistic regression.
it's talking about an equation, and that's not what that is. So maybe the other one. Let's see if the other one works.
The diagram you provided
go.
depicts a Siamese neural network architecture. This type of network is particularly useful for tasks that involve finding the similarity or relationship between two comparable things, such as images, sentences, or videos. Here's a detailed breakdown of how it works and its applications. Components of the Siamese neural network. 1. Input pairs x1, x2. These are two input vectors or data points that need to be compared. For example, in a face verification task, x1 and x2 could be different images of faces. 2. Network A. This represents a neural network that processes each input. Crucially, the same network with the same parameters, weights, and biases is used for both inputs. This shared network ensures that the features extracted from both inputs are comparable. The network typically consists of several layers, convolutional, pooling, fully connected layers, etc., designed according to the type of input data. 3. Similarity function. After both inputs are processed through network A, their outputs, feature vectors, are passed to a similarity function. This function computes a metric that quantifies the degree of similarity between the two feature vectors. Common similarity functions include Euclidean distance, cosine similarity, or more complex neural network architectures that can learn the best way to compare feature vectors. 4. The output of the similarity function is a similarity score that quantifies how similar the two inputs are according to the learned features and similarity criteria. This score can be used to make decisions, such as whether the inputs are the same or different, or to rank inputs based on similarity. Functionality and workflow. Feature extraction. Both inputs are passed through the same neural network, network A, which extracts meaningful features from each. Using the same network ensures that the features are comparable. Comparison. The extracted features are then compared using the similarity function. The nature of this comparison depends largely on the task at hand. Output generation. The result is a similarity score that reflects how close or far apart the two inputs are in the learned feature space. Applications. 1. Face verification, used to determine whether two images are of the same person. 2. Signature verification. Comparing signatures to verify identity. 3. Matching items in different images, identifying the same item across different scenes or lighting conditions. 4. Anomaly detection, comparing an object against a reference to detect anomalies or deviations. 5. Recommendation systems, comparing user profiles or items to make personalized recommendations based on similarity. Summary. Siamese networks leverage the power of neural networks for feature extraction combined with a mechanism for directly comparing those features. This makes them highly effective for similarity and comparison tasks, particularly in cases where direct feature-to-feature comparison is essential for performance. The ability to learn complex patterns and nuances in data also makes them superior to more traditional comparison methods, which do not involve learning.
All right, perfect. So, interestingly, a Siamese network architecture can be used to verify the coincidence of pictures the model has never seen before, which introduces the idea of one-shot learning, which we will discuss later in more detail. This is possible because what the model has learned is the ability to find similarities in the pictures, not the pictures themselves. Of course, this is contextualized to a particular type of picture. Let's say a person's face with white background. If pictures of different types are used, pictures of dogs in a model trained to verify human faces, very likely that the model will not work. All right, so the next one is graph neural networks. Data can be represented in multiple form factors. Images are usually represented as a matrix of numbers, as a 2D matrix with width, height, or 3D width, height, 3 colors if you have RGB channels. Aligned with that representation, an optimized neural network architecture, as we have studied, CNNs, takes advantage of its structure and properties. Similarly, for sequences like texts or time series data, we have RNNs, recurrent neural networks, and their different derivatives that are optimized to take advantage of the nature of those sequences. And CNNs are convolutional neural networks. Graphs are a pervasive data representation key in many disciplines like social analysis, biology, and of course, networking and cloud. A graph represents a set of entities, nodes, and their relationships, edges, or links. A data center network topology is a graph. A microservices service mesh is a graph, and your network BGP connectivity can be represented as a graph. Graphs are a ubiquitous and powerful data representation because they can capture the entities and their properties and how entities relate with each other. Graphs are everywhere, and in networking and cloud infrastructures are fundamental to describe, capture, and explain dynamic behaviors. All right, so let's see what it's so cool that ChatGPT can come up with the right answer based on such like sparsely drawn diagrams.
The image you've uploaded depicts a simple directed graph structure, which is a fundamental concept in graph theory and has numerous applications in various fields such as computer science, biology, social sciences, and more. Here's a breakdown of the components shown in the diagram and their significance. Components of the graph. Node. A node, also known as a vertex, represents an entity or an object. The graph in the image has several nodes, with the central node highlighted as an example. Each node is a fundamental part of the graph structure and can represent data points such as people, computers, intersections on map, or any other discrete item depending on the context of the application. Edge. An edge represents a connection or relationship between two nodes. In the context of the provided diagram, the edges are directed, meaning that each edge has a direction indicated by the arrow. This directionality implies that the relationship is not bidirectional. For example, in a social media setting, a directed edge might represent a one-way follow or a one-sided interaction. Functionality and applications of directed graphs. Directionality. The arrows on the edges specify the direction of the relationship, which is crucial for understanding many real-world systems where interactions are not always reciprocal, such as web-page links, hypertext links, citations in scholarly articles, or followers on social platforms. Network analysis. Directed graphs are extensively used in network theory to analyze the reachability between nodes, find the shortest paths, or explore network dynamics such as the flow of information or contagion spread in social or biological networks. Flow networks. In scenarios like traffic systems, flow networks use directed graphs to model and analyze traffic flow and to optimize routes and reduce congestion. Nodes represent intersections or endpoints, and edges represent paths or streets, with direction indicating the permissible travel direction. Dependency analysis. Directed graphs are pivotal in representing dependencies, such as prerequisite structures in education courses, task scheduling and project management, or dependency resolution in software packages. Analytical operations. Graph traversal. Techniques like depth first search, DFS, and breadth first search, BFS, are used to traverse or search elements in graph. These are foundational for more complex operations like cycle detection, connectivity checks, or pathfinding. Topological sorting. This is a linear ordering of vertices such that for every directed edge UV from vertex U to vertex V, U comes before V in the ordering. This is particularly useful in scheduling tasks where some tasks must be performed before others. Strongly connected components. Identifying strongly connected components in a directed graph helps in understanding the modular structure of the network, which can be useful in simplifying analysis by collapsing strongly connected components into single nodes and focusing on the interactions between these components. The simple representation in the diagram offers a clear and concise introduction to the structure of directed graphs, providing a visual and conceptual basis for understanding their broader applications and significance in complex systems analysis and other algorithmic processes.
Alright, so a graph representation of data differs entirely from a matrix, a vector, or a sequence. Therefore, we may intuitively think that we may need an optimized version of a neural network architecture to deal with graphs and take advantage of the information that graphs contain, which conventional or standard architectures may not be capable of. That leads to the concept of graph neural networks, GNN. A graph neural network can learn not only from the data in the nodes, but also from the relationships among them and build or extract patterns from them. We can use a GNN for multiple use cases, to name a few. Node classification. Your network is built out of several nodes, which you may want to classify according to specific criteria. Like in usual classification use cases, you may have a sample dataset with labels that would allow you to build a model that, once trained, can be used to generalize and classify other nodes accordingly. Imagine a scenario where our graph represents the different events happening in your network. An event is a node, and we would like to classify whether the impact of an event is high or low. We may have categorized in the past several such events. However, ultimately, it is not the event that makes it highly severe or low, but other events that also happen around it that may be related. Given the relationships, we could train a model that estimates any new such instance of an event and how severe it is expected to be. This is an example of node classification. Link prediction. Your graph contains a set of nodes and edges, links, but there could be cases where certain relationships represented by the edges are not present, but they should be. This type of use case aims to predict those missing edges and somehow complete the graph. Imagine, for example, that we represent the interactions between a user in our network and the different systems as a graph. Each user interaction is represented as an edge containing the user node and a system node. Examples of systems could be your DHCP, DNS, web proxy, etc. Different users might have different behavior patterns that will result in different structures in the graph. Let's suppose that, for whichever reason, the interactions between one user and a particular system fail, and therefore in our graph of interactions, we miss such edges. We might have a model that allows us to identify such missing connections and proactively raise alerts that such users are not working as expected. Graph level classification, prediction, or clustering. If we zoom out, we can see the graph as an entity. We no longer focus on the specific nodes or edges within the graph, but in the graph itself. When we consider the graph as an entity, we can start considering use cases such as classifying a graph into a particular class, predicting a specific property given an entire graph, or potentially finding similarities among graphs and clustering them together. Let's suppose a scenario where we are collecting network events and we are somehow, let's ignore the how for the moment, connecting those events that are highly related. Over periods, there may be clusters of those events together. These are usually referred to as incidents in monitoring and observability terminology. We could think of each incident as a subgraph or simply a graph with a set of nodes, events, connected with others by the degree of relationship. We have, therefore, a number of graphs, many of which may be similar, which we could potentially cluster them to identify patterns, etc. Graph neural networks, GNNs, are complex entities in how they work and operate internally. I will not go into all the details, but give a high-level intuition. In CNNs, convolutional neural networks, or RNNs, recurrent neural networks, we have seen there are mechanisms as the data flows through the different layers to aggregate and selectively extract information, feature selection, from the incoming data. We need a similar mechanism in a GNN that somehow leverages the fact that it is a graph, meaning nodes have certain relationships. One way to capture the graph topology would be to force a process by which information flows through the graph. Somehow, that information can be transformed similarly to how in a CNN the feature maps get transformed via the convolution and the filters. In GNNs, a message passing scheme is implemented that enables such information flow and transformation. The topology around a node, its neighbors and their neighbors, and the different links represent different paths of data transformation that the GNN will use to compute its weights. Alright, and we've got a graphic for that, so I'll get an explanation from ChatGPT. I think this is useful. So the key takeaway, there is a strong potential in our networking and cloud field about leveraging GNNs.
The image you provided illustrates the concept of graph neural networks, GNNs, particularly focusing on the message passing mechanism that enables such networks to process graph structured data. This diagram clearly shows how information is aggregated from neighboring nodes to update the representation of a given node. Here's how it works and why it's significant. Components explained. Original graph structure. The left side shows a simple graph with nodes labeled ADF and directed edges connecting them. This structure represents relationships or interactions between entities. Focus on node B. In the transformation to the right side of the image, attention is focused specifically on node B. This node acts as a central point receiving inputs, messages, from its neighboring nodes A, C, D, E, F, based on the graph structure. Message passing. Message passing is the process through which information, features or signals, from nodes connected to B, either directly or indirectly, are passed to B. Each node sends a message influenced by its features or state. Aggregation function. Once messages reach node B, an aggregation function is applied to these messages. This function might be a sum, mean, or a more complex operation designed to best combine the features from B's neighbors. The choice of aggregation function can significantly impact the performance and capability of the GNN. Output graph structure. On the right side, you see the resultant graph after the aggregation process at node B. The transformation illustrates how node B's state is updated based on its neighbor's information, central to GNN functionality. Significance and applications. Node feature update. In GNNs, each node updates its features by aggregating information from its neighbors, which allows the network to learn complex patterns across the graph. This updated feature can be used for node-level predictions or classifications. Learning dependencies. GNNs effectively capture dependencies and relationships in data structured as graphs, making them suitable for social network analysis, recommendation systems, and molecular chemistry, where entities are interrelated in non-Euclidean spaces. Versatility. GNNs can be used in various tasks, including node classification, link prediction, and graph classification. They are particularly effective in scenarios where the relationship between entities significantly influences the outcome. Further detail. Edge directions. Depending on the type of GNN and the specific task, the direction of edges can significantly affect how messages are passed and aggregated. Some GNN architectures might consider the direction as crucial, while others may treat the graph as undirected. Learning over iterations. Typically, a GNN will perform the message passing and aggregation steps multiple times, each time updating the node representations. Through several iterations, nodes accumulate increasingly comprehensive information from their extended neighborhood, not just their immediate neighbors. This diagram effectively encapsulates a fundamental aspect of graph neural networks, demonstrating how local node information is aggregated to learn global structures within the graph, thereby enabling the network to make informed predictions and decisions based on the graph data.
Alright, so continuing with the key takeaway, there's a strong potential in our networking and cloud field about leveraging GNNs, specifically graph. Yeah, and that makes sense because there's already a lot of graph algorithms, such as Dijkstra's algorithm, shortest path first. Yeah, that makes sense. Therefore, it is important that you get familiar with the key concepts and fundamentals. So let's go above and beyond and say, tell me the key concepts and fundamentals of graph neural networks.
Graph neural networks, GNNs, are a sophisticated class of neural networks designed to handle data represented as graphs. This makes them uniquely suitable for applications where data points have explicit relationships and interdependencies that significantly affect the underlying data patterns. Here's a detailed breakdown of the key concepts and fundamentals of GNNs. 1. Graph structure nodes. In a graph, nodes represent entities or objects. Each node can have features that describe its properties. Edges. Edges represent relationships or interactions between nodes. These can be directed, one-way relationships, or undirected, two-way relationships. Graphs. A collection of nodes and edges forms a graph, which can be used to model complex systems like social networks, molecular structures, or communication networks. 2. Message passing mechanism. The core computational principle in GNNs is a message passing mechanism where nodes send information to neighboring nodes. This mechanism typically involves two key steps. Message calculation. A function calculates a message for each edge based on the features of the nodes it connects. Aggregation. Nodes aggregate the messages received from their neighbors. This aggregated information is then used to update the node's features. 3. Aggregation functions. Aggregation functions play a crucial role in GNNs as they determine how the features from neighbor nodes are combined. Common traces for these functions include sum, mean, max, or more sophisticated neural network-based functions. The trace of aggregation function can impact the GNN's ability to capture different types of graph structures and features. 4. Node embeddings. After several rounds of message passing, each node ends up with an embedding, a vector that encapsulates not only its own features but also information about its neighborhood. These embeddings can be used for tasks like node classification, link prediction, or even entire graph classification. 5. Training GNNs. GNNs are typically trained using backpropagation, similar to other types of neural networks. However, due to the graph structure, the computation graph of the neural network is defined by the edges of the input graph, which can make training particularly challenging in large graphs. 6. Learning graph level representations. Besides learning representations for individual nodes, GNNs can also aggregate node embeddings to form a single representation of an entire graph. This is useful for tasks such as graph classification where the entire graph needs to be classified into categories. 7. Challenges in GNN scalability. Processing large graphs efficiently with GNNs is challenging due to the need for handling extensive neighborhood aggregation. Oversmoothing. Repeated message passing over many layers can cause node embeddings across the graph to become indistinguishable, a phenomenon known as oversmoothing. Dynamic graphs. Many real-world graphs are dynamic, where nodes and edges can change over time. Adapting GNNs to handle such dynamic graphs is an ongoing area of research. Applications of GNNs. Social network analysis, for detecting communities or recommending friends. Bioinformatics, for predicting protein interfaces and interactions. Chemoinformatics, for predicting molecular properties or biological activities. Recommendation systems, where items and users are nodes and interactions are edges. Graph neural networks represent a significant advancement in the way neural networks can incorporate and process relational data. Their ability to learn from the structure and features of graphs makes them powerful tools for many modern AI challenges.
Alright, so that's that. Now give me some ideas for how graph neural networks can be applied to the field of network and cloud engineering.
Graph neural networks, GNNs, hold significant potential for application in network and cloud engineering, areas where the relationships and interactions between components are critical to performance, security, and management. Here are several innovative ideas for applying GNNs in these fields. 1. Network traffic prediction use case. GNNs can be used to model traffic flow across a network by treating network nodes, routers, switches, and connections, data paths, as graph elements. Benefits. This can help predict congestion points, optimize routing protocols, and enhance quality of service, COS, by predicting future traffic patterns based on historical data. 2. Anomaly detection in network traffic use case. By modeling network traffic as a graph with nodes representing endpoints and edges representing communications, GNNs can detect unusual patterns that might indicate a security breach, DDoS attack, or network failure. Benefits. Early detection of anomalies can trigger alerts for timely intervention, thus enhancing network security and resilience. 3. Network optimization and configuration use case. GNNs can optimize network configurations for performance by simulating different network setups and predicting their outcomes. Benefits. Automatically optimizing configurations can lead to better resource utilization, improved performance, and reduced costs. 4. Resource allocation and cloud networks use case. In cloud computing environments, GNNs can manage the allocation of resources, like CPUs, memory, and storage, by modeling the cloud infrastructure as a graph where nodes represent computational resources and edges represent their connections. Benefits. This approach can enhance the efficiency of resource utilization, balancing load effectively and reducing bottlenecks. 5. Fault detection and management use case. GNNs can predict points of failure in a network by learning the typical signal patterns of nodes and edges in a graph-based representation of network infrastructure. Benefits. Proactive fault detection helps in maintaining high availability and reliability of network and cloud services, minimizing downtime. 6. Cloud security use case. Use GNNs to detect patterns of access and use that might indicate unauthorized or malicious activity within a cloud environment. Benefits. Enhancing cloud security protocols by identifying and responding to threats in real time based on the relationships and interactions within the network. 7. Service virtualization and network function virtualization, NFV, use case. GNNs can optimize the deployment of virtual network functions and services on a network by understanding dependencies and performance metrics across different nodes. Benefits. This leads to more efficient virtualization strategies, improving performance and reducing costs. 8. Dynamic scaling and load balancing use case. GNNs can dynamically scale resources and balance loads across a cloud network by continuously analyzing the demand at each node and edge in the network graph. Benefits. This ensures that the cloud infrastructure can adapt to varying loads efficiently, maintaining performance without over-provisioning resources. 9. Topology discovery and management use case. GNNs can help in automatic topology discovery and management by learning the structure and changes in the network graph over time. Benefits. Keeping an up-to-date model of network topology is crucial for effective network management and planning. By leveraging the inherent graph structure of network and cloud systems, GNNs provide a powerful toolset for enhancing monitoring, optimization, and security. Their ability to learn and predict complex relationships within data makes them ideally suited to these highly interconnected environments.
Now, for each of these, show me a brief example of code using whatever tool is necessary, preferably Python, if there's a choice, for how I could implement these in the real world. All right, and so that's the end of this part. So the next part is generative versus discriminative techniques. So
Implementing graph neural networks, GNNs, for network and cloud engineering applications can be quite sophisticated, but Python libraries such as PyTorch, GeoMetric make it easier.
PyTorch.
Here's a brief example for each application mentioned, using Python and PyTorch, GeoMetric to give you a starting point for how these could be implemented in real-world scenarios. 1. Network traffic prediction. Here's an example to model network traffic. 2. Anomaly detection and network traffic. An example using a GNN to detect anomalies. 3.
Cool.
Network optimization and configuration. Example to optimize network configuration. 4. Resource allocation and cloud network. Simplified example for resource allocation. These snippets provide foundational understanding, but remember that real-world applications often involve additional complexities such as integrating with existing systems, handling real-time data streams, and ensuring robustness and scalability. Each example assumes basic familiarity with PyTorch and PyTorch GeoMetric, two powerful tools for building GNNs.
All right, so the next section is an all-new section. It's generative versus discriminative techniques. So I think I'm going to cut the video here. This is a logical place to cut it, and then have that be in its own video. So thanks for watching, and stay tuned for the next one.